Hi, this is Ilaria Mondello, and this is a talk for the virtual workshop on Ricci and Scalar curvature in honor of Misha Gromov. I would like to thank the organizer for giving me the opportunity to give a talk in this nice workshop. Today I'm going to talk about a joint work with Kazuo Akutagawa, which concerns the non-existence of Yamabe metrics in a singular setting. The Yamabe problem consists in trying to find a conformal metric in some class of a given Riemannian metric with constant scalar curvature. Often, in order to try and solve this kind of problem, you need to minimize a functional, in this case, the Yamabe functional. And so a Yamabe metric is a metric which minimizes the Yamabe functional. It is a minimizing metric. It is well known that in the case of compact smooth manifold, there always exists a Yamabe metric. So you can always minimize the functional and find a minimizer. In 2010, Jeff Viaclovsky presented an example of a manifold with one isolated conical singularity for which the same is not true. So in presence of conical singularities, a Yamabe metric may not exist. With Kazuo Akutagawa, we found new examples of this phenomenon, in particular with codimension 2 conical singularities. In the first part of the talk, I'm going to give some essentials on the Yamabe problem in the smooth setting, so compact smooth manifold of dimension larger than 3. I will explain and motivate which is the singular setting that we are going to deal with, and give the main result that we have with Kazuo Akutagawa. At the end of this part, I will give some references in case you want to pause watching the video and go and have some reading. In the second part of the talk, I will give the precise definitions for the conical singularities of codimension 2 that we are going to study, and also for stratified spaces, which is a slightly more general setting in which some of the results do hold. I will give some definition about the Yamabe problem on these spaces, stratified spaces, and the known results that are needed in order to prove our non-existence result. In the last part of the talk, I will give a sketch of the proof of the non-existence result, some consequences, and I will present some open questions. So the Yamabe problem is one of the problems at the origins of geometric analysis, and it started from a question of Yamabe in the 60s. The idea is, can we modify a bit a given Riemannian metric in such a way that the new metric has constant scalar curvature? What does it mean to modify a bit? In this case, it means using conformal changes. So one multiplies the given metric by a conformal factor. And so this change of metric doesn't change angles between curves, okay? So can we find a conformal metric in this conformal class such that the new metric has constant scalar curvature? The question was asked in dimensions larger than 3 because thanks to Poincaré uniformization theorem, it was already known in dimension 2 that there always exists a conformal change that makes the scalar curvature constant. In order to solve this problem in dimension larger than 3, it took around more than 20 years to give an answer, and the answer is yes, you can also find a conformal metric with constant scalar curvature for a compact smooth manifold of dimension larger than 3. And this is due to the work of Trudinger, Aubin and Schoen. The way of solving this problem, one of the ways to solve this problem is to use a variational approach. So the idea, as I said before, is to introduce a functional such that if you minimize this functional, you find a metric which has constant scalar curvature. So the Yamabe functional is given by the quotient of the total scalar curvature, the integral of the scalar curvature over the whole manifold, and the volume of the manifold at the good power. When you use the transformation law for the scalar curvature under conformal change that you can find in Best's book, Einstein Manifolds, you can replace this by something that depends only on the conformal factor, and you get this functional, and it is the same to minimize this one or this one. So one can define the Yamabe constant as the infimum of the Yamabe functional over all conformal metrics or over all smooth functions that do not vanish. This is a conformal invariant, of course. And now, if you find a metric such that the Yamabe functional computed on this metric is exactly equal to the Yamabe constant of the manifold, then this is called a Yamabe metric, so a minimizing metric, and this metric has constant scalar curvature. So if you find a Yamabe metric, you find a metric of constant scalar curvature and you solve the Yamabe problem. If you have a Yamabe metric, we call its conformal factor U a Yamabe minimizer. So the work of Trudinger, Aubin and Schoen showed that a Yamabe metric always exists in the setting of compact smooth manifolds of dimension larger than 3. How did they do that? First, Trudinger showed that a Yamabe metric exists and it is unique when the Yamabe constant is less than 0. Later on, Thierry Aubin showed an important inequality that was used it was used a lot after that, which is the Aubin inequality, and it showed that the Yamabe constant of a manifold of dimension n is always less or equal than the Yamabe constant of the sphere, the round sphere of the same dimension. Why this? The idea is that you take functions, U conformal factors that are only supported on a small ball. So you get, when you minimize on functions that are supported on a small ball, you get something which is bigger than the whole Yamabe constant. And when you make the radius of the ball go to 0, you get something which is closer and closer to a ball in a Rn. And this leads to this Yamabe constant of the sphere. So you get the Aubin's inequality, and he also showed that when the inequality is strict, a Yamabe metric does exist. He also showed some examples in which found some examples for which the strict inequality actually holds. After the work of Aubin, one of the questions was what happens in case of equality between the Yamabe constant of the manifold and the Yamabe constant of the sphere. And this was solved by Ricci and Scalar in 1984. Thanks to the positive mass theorem he proved with Yau, he was able to show that if a manifold has Yamabe constant exactly equal to the Yamabe constant of the sphere, then you can find a conformal diffeomorphism between the manifold and the round sphere, and thus, when you pull back the round metric of the sphere, which is a Yamabe metric, you find a Yamabe metric on the manifold. Good. We are going to be interested in studying this kind of problem on some singular manifolds, so manifolds with conical singularities, and I would like to give some motivation for this singular setting. So it is very easy to find singular manifold in differential geometry, in Riemannian geometry. For example, when considering quotients of smooth manifold. Here you see an American football, so a surface with two isolated conical singularities, and it is just obtained as a quotient of the sphere by the group generated by a rotation around an axis, which has two fixed points that give the two isolated singularities. Moreover, when you study Gromov-Hausdorff limits of smooth manifolds, whenever the limit exists, it is not necessarily a smooth manifold, but it is a metric space, which carries singularities. In particular, if you consider a sequence of smooth manifold with a uniform lower bound on Ricci and a non-collapsing assumption, it is known that this sequence, well, up to a subsequence, you have convergence to a metric space, and moreover, this metric space has singularities which have at least codimension 2, almost everywhere, and the singularities are modeled on codimension to conical singularities. This means they are modeled on the product of a Euclidean space of dimension n-2 and a two-dimensional cone. So we're going to be interested mostly in this kind of codimension to singularities, product of Euclidean space and two-dimensional cones. So let's start to fix the notation, and I will tell you what I mean for a two-dimensional cone. I mean a product between R plus and a circle of radius A. So the metric here is a metric in polar coordinates. R is the distance from the vertex of the cone. And here you have a parameter A, which depends on the radius of the circle. If you take A equal to 1, you don't create any singularity. It is just R2 with polar coordinates. When A is different from 1, you actually get a cone with some angle, which is 2 pi A. Okay, so when A is less than 1, this is exactly what you imagine as a cone. You have something of, you need to imagine a circular sector of angle 2 pi A, and you identify the two radii, and you get a cone with a vertex. And this cone is a two-dimensional Alexander space with positive curvature in the sense of Alexandrov, even if in the Riemannian sense it is flat. When A is bigger than 1, you also get a cone, but it's less similar to what you imagine as a cone. You need to think of a sheet of paper, and you cut it along a line, on a half line, and in this cut you can add some portion of angle, and this will give you a cone, again, of angle bigger than 2 pi. And in this case, the space is also an Alexander space, but the curvature is not bounded from below, it is negative. And our examples of non-existence will be, will have singularities of angles larger than 2 pi. We will need singularities of codimension 2, as I was saying. So the idea is that you take your Rn and you decompose it in the product of Rn minus 2 and R2. On R2, you can consider this metric, this conical metric that we just introduced. And so on the product of Rn minus 2 and a cone, you can consider the product metric between your Euclidean metric on Rn minus 2 and the conical metric. So in this case, you get an Rn, which is singular along Rn minus 2. So here you have the picture in dimension 3. In dimension 3, you will have R cross a cone. So you create a singularity, a conical singularity along the line R. At each point here, you need to imagine that you have a cone. So a manifold with conical singularities of codimension 2 will be singularities modeled on this product. So here's a picture, and you need to imagine that this is dimension 3, and this is a curve in the three-dimensional manifold. So here it is a singular curve, and the idea is that at each point here, you will find a neighborhood, a tubular neighborhood of the curve, which is not smooth. Usually a tubular neighborhood would be the product of an interval and a disk. But here, since we have singularities, a tubular neighborhood of a point here will be the product of an interval with a two-dimensional cone with some angle. And we will also need to define what a metric is on this kind of manifolds. And usually the metric won't be defined on the singularities, it will be defined away from the singularity, and it will have the good asymptotics when you get closer to the singularities in order to get conical singularities, okay? Another example, which is going to be very useful in the following, is the one of singular spheres. So consider the unit sphere and the stratigraphic projection from the sphere minus the north pole to Rn. Then we can define this function on Rn and a conformal metric to the singular metric Ga that we just defined. So here, remember, you give to Rn a conical singularity along an Rn minus 2. Then you pull back this metric on the sphere, and you get another metric on the sphere. When A is equal to 1, remember this metric is just the Euclidean metric, and when you pull it back on the sphere, you just get the round sphere, the usual round sphere without any singularity. When A is different from 1, this metric HA carries conical singularities along a codimension 2 great circle. The idea is that if you have a singular Rn minus 2 here, when you pull back this conformal metric on the sphere, you are closing up the singular Rn minus 2, and so you get a codimension 2 singularity on the sphere. You can imagine just the case of dimension 3, and then you will have a singular equator, okay? Now, the Yamabe problem in this case, as I said, the metric will be defined away from the singularities. So the scalar curvature is only defined away from singularities. So the question will be, can we find a conformal metric which has constant scalar curvature away from the singularities and not at the singularities? And we will need to define the appropriate Yamabe functional to check it is well defined. And another way to formulate this problem is, does there exist a Yamabe metric? Okay, so in the case of conical isolated singularities, it is known that the Yamabe problem does not always admit a solution. Indeed, Jeff Viaclovsky in 2010 constructed examples of 4 manifolds with 1 isolated singularities for which there is no Yamabe metric in the conformal class of a given metric. How did he do that? He constructed a conformal compactification of a hyperkähler 4 manifold, which is asymptotically locally Euclidean. Asymptotically locally Euclidean means that it is an open manifold, which at infinity looks like a quotient of Rn, in this case R4, by a discrete group, a finite discrete group, and here the order needs to be bigger than 1. Otherwise you won't get any singularity in the compactification. And one interesting thing is that the metric Gn on this conformal compactification is already Einstein away from the singularity. So it has constant scalar curvature, but itself it is not minimizing, and there are no other minimizing metrics in this conformal class. What we prove with Kazuo is an analogous result in the case of codimension 2 conical singularities. We consider the singular spheres, so the spheres with the metric Aj that put a conical singularity of codimension 2 along a grid circle of codimension 2. And when the angle is bigger than 4 pi, so this parameter here is bigger than 2, this singular sphere does not carry any Yamabe metric. Again, the metric Aj is Einstein away from the singularity, so it has constant scalar curvature, but it is not Yamabe, and there is no other minimizing metric in its conformal class. We conjecture that the same is true when A is between 1 and 2, so angle between 2 pi and 4 pi, and I will explain at the end of the talk why it is more difficult to get the same result between 1 and 2. So here's some references if you want to have some reading. The first 2 papers are survey papers. The first one is about the Yamabe problem on compact smooth manifolds, and there are a lot of references in it, so it's very nice. The second one is a Number-Wolfach report about the Yamabe problem in the case of stratified spaces, and if you want something longer that better presents stratified spaces, you can find it in my PhD thesis. And those are all the research papers that we are going to cite in the rest of the talk, in particular Viaclovsky result about non-existence, and all the previous results that led to the proof of our result with Kazuo Akutagawa.